Hey everyone. So it looks like it's about time for us to get started. So let's go ahead and do that. So welcome to the evolution of functional programming in C++. A little bit about me. I'm a functional and systems programmer focused on programming languages like Haskell, C, and C++. Here are my socials. You can generally find me on all the major platforms. Feel free to reach out to me at any time, especially after the conference, to ask any doubts you may have about this topic. I'd love to discuss more C++ with you all. So let's go over the agenda for today. First, we're going to talk about the origins of C++ and its ethos as a programming language. Then we're going to discuss the meat of this presentation, which is going to talk about how the ISO C++ standards have gradually facilitated the ability of you, the programmer, to incorporate functional programming concepts into your C++ programs. In particular, we're going to focus on understanding the benefits of each functional programming or FP feature, and we're going to engage in some comparisons with Haskell as a purely functional programming language. And then finally, we're going to round out the talk by talking about FP and what it'll look like in C++ 26 and beyond. So what is C++? Well, it's a programming language that has been inspired by the powerful type checking and abstractions provided by the programming language Simula. It was actually used by Dr. Bjorn Stroustrup in his PhD thesis work for implementing a simulator for distributed systems. Now, it turned out that although Simula was very nice for abstractly representing the needs of this distributed system, it was far too inefficient for it to run effectively on a mainframe system he had to share with other university students. So he found himself having to rewrite the whole program and debugging it and turning it to BCPL, which is a very low-level programming language. So come time when Dr. Strostrup had to work at Bell Labs in Murray Hill, New Jersey, he once again found himself writing a distributed system. And he realized that he couldn't quite repeat the Herculean effort of writing such a system in a low-level language like BCPL. And that's really the impetus for C with classes, now known as C++. So overall, what can we say about C++ as a language? Well, it is a systems language built to solve real-world programming problems. It offers lightweight to zero-cost abstractions for effectively modeling concepts from any problem domain. And it should scale to handle the complexity of any problem you might face as a programmer. So let's talk about the first ISO C++ standard, which is C++ 98. The core functional features of this release boil down to essentially functions as first-class citizens and this idea of generic programming. And we can further expand this concretely into function pointers, function references, pointers to members, function objects, and templates. So let's start with the first one, which is function pointers. Now, before we get into that, let me explain what I mean when I say functions as first-class citizens. The basic idea of this is that we can pass functions to functions, return functions for functions, and bind functions to names. And so when we talk about function pointers, they're really a holdover from the language C, off which C++ is based. And arguably, I'd say they make functions as a notion a first-class concept in the language C++. And I'll say the key benefit of something like function pointers is that they allow you to refactor high-level algorithms out of concrete implementations. So let's see what we mean by that exactly. Now, of course, there's no more real-world example than that of course, sorting lists, right? So let's say your boss comes up to you and says, you know what, Abel, I need you to sort a list and do it two ways. We need to maybe A/B test Lomuto quicksort and Hora quicksort. We'd like for it to be maintainable. And so you as a programmer are left wondering, what exactly do I do? So here's our initial attempt. So here we have a std vector of ints into which we're pushing back a number of elements. And then we have another std vector into which we're pushing copies of all those elements to try our other algorithm. Then we're actually testing on both quicksorts, Lomuto quicksort and Hora quicksort. And you can see here for Hora quicksort, we have a driver, which calls into the impl, which passes not only the std vector, but also low and high indices. And then the actual impl, which contains the core logic of partitioning, returning midpoint, and then reversing to left and right sides. And then similarly, we have the Hora partition function, which we elided here for simplicity's sake. And similarly, we have Lomuto quicksort, which has a driver, which calls into the impl. The impl has a core logic, And low partition is the core strategy behind this quicksort. So what we notice here is that essentially we have the same driver skeleton, same algorithm skeleton, in which we invoke the partition function to get the midpoint, and then recursion to the left and right sides. And really the only different thing is the partition strategies. So how about we try extracting out that function or strategy as a parameter? So here, instead of defining two different types of quicksort, we've defined a single type of quicksort which not only accepts a stood vector, but also a pointer to a function representing our strategy. So on line 63 and 64, we pass pointers to Lamuta partition and Bohr partition respectively. So once again, we have a main quicksort driver, which now accepts a pointer to a function argument, which is our partition strategy. And also we have, once again, a actual impl, which recurses into the left and right sides after partitioning. And of course, our partitioning strategies can remain exactly the same. We don't have to touch that. So the benefit of what we've done here is the sorting algorithm is now separated at a high level from the concrete partitioning strategy. So the benefit of this is the code can be refactored to, or extended with new strategies without unnecessary source code bloat. The cons, of course, are that we have some parameter drilling of this function pointer, and then we invoke the runtime cost of this function pointer dereference. So now let's go on to our second feature, function references. Very similar to function pointers, except that they come with those features that we know and love from references, which are that they cannot be reseeded and they can never be null. So let's revisit how we sort using function references. So here, instead of passing pointers to functions, I'm just passing references to these functions by just simply stating their names. And then I've altered the quicksort driver to take a reference to a function rather than a pointer. And then likewise, I've updated the corresponding parameter of the quicksort impl. And everything else was the same. So let's skip ahead a bit and talk about function objects. So to motivate this conversation, I need to introduce the functional header. The functional header defines a set of function objects that compose well with what I'll call function algorithm templates. A function object is really no more than an object for which operator parentheses or the call operator is defined. And the neat thing about function objects is that they introduce this idea of closures and partial application into the world of C++. So let's do another refactor. The key principle here will be allowing the user to pick the type of customization as they've been doing before. So now we've templatized our quicksort function. I know we're skipping ahead a bit, but we've templatized it using a type name partition strategy so that it can accept any callable object or type. So the quicksort driver now has a partition argument of type partition strategy from our template parameter. And then likewise, we templatize the impl using a type name partition strategy and introduce a corresponding parameter. And basically the logic remains the same. Partition will be used as whatever callable is passed to the function template upon instantiation. So the benefit of doing this refactor is that the client code stays exactly the same, right? So we can continue using function references like before, nothing changes on the client side. But the real benefit of doing this pretty little refactor is that we can now pass function objects to quicksort to specify the partition strategy. So how it looks like is as follows. Here we're defining a struct Lamuta partition, which is a call operator, which takes a stub vector, low and high indices, and then returns the midpoint after partitioning. And then likewise, we define a function object called Bohr partition, which does the same thing except using the Bohr partitioning strategy. And so now, when we do these two invocations of quicksort, we instantiate an instance of Lamuta partition, Bohr partition, respectively, to pass them to the function template. So the benefit of this overall is that we get potentially better inlining due to this use of template instantiation, stateless objects. We do get potentially more binary bloat because of all the template instantiation. But overall, I'd say function objects really come to shine when they allow us to emulate closures by capturing values or variables from the surrounding environment upon construction. So let's see an even better example. So to motivate this part, here I'm defining a struct called addNumber, which has a private int member variable number. Upon construction, you initialize the number variable, and then it has a call operator defined, which takes another number and adds it to the privately stored number member variable and returns the result of the addition. So the neat thing here is if, let's say, you want to specify a declarative transformation of a std vector of ints and add, say, some number x to each of those elements to get a new std vector, what we can do is invoke the std transform algorithm passing in our std vector, and then specifying as our transformation in line 25 as the result of add number of x, which instantiates this function object using the surrounding lexical variable x. So essentially, you're capturing x from the surrounding environment to form a closure of sorts, so that variable or number is added to each of the elements of this vector. Now, in that example, there's a slight problem, which is that there's already actually a function object in the standard library that expresses this desired computation. However, its signature is a bit too general. So the idea here is, can we avoid reinventing the wheel? So, of course, what we're talking about is this function template known as std+. So here we're specializing std+ to the type of int, so that we're able to accumulate or reduce a std vector of ints into a single summary value. So we're using std+ as this binary reduction operation. So the solution to our original problem is to specialize std+ with the parameter bound to the argument we already have on hand. So here we're invoking the std transform as before to transform our list of integers, except now we're invoking std bind first. So std bind first takes in as its first parameter a callable, and then takes in as its second parameter an object or variable to which we bind the first parameter of this binary function. So now we're binding x to the first parameter of the binary function std+ of int. So similar to bind first, there's actually bind second, which specializes a function object by binding the second argument. And I'll note that there are many other function objects in the functional header, like -t equal to, that you can use to, in conjunction with these other things like bind first, express declarative computations. So now let's go back to pointers to members. I won't go on this too long, but I'll note that they can easily be turned into function objects that actually take an object as a parameter and return a member as a result. So functional also provides function objects and function templates like memfunt and memfun for exactly this purpose. So now we get into templates for real. So this idea of generic programming of templates is that templates allow you to specify generic recipes out of which you can bake concrete classes or functions. And the neat thing in C++ is that you can specialize them to a particular recipe in the case of specific classes. And we'll see what that means in a moment. So here's a somewhat more realistic example this time. So here I'm defining a templatized stack, which has a type name t, and it comes with a standard pointer to head in its private implementation. And then it exposes a default constructor which initializes with a single value, and then the standard push, front pop, and then the destructor. So of course, a user can use this like any other stack. They can push a bunch of elements onto the stack and then pop them back out in reverse order, and you'll get the correct result. Now, this is C++, however, so we can also do interesting things like specialization. So here I'm specializing the type name parameter to bool. So I'm creating a new instantiation of the function template stack so that's specialized to bool. And the reason why I'm doing that is we know that in case of bool, there's only two values, true and false. So we can essentially get a space optimized version of stack by essentially treating it as a bit set. And that's what we're doing here by redefining the internals by creating a new private member bit set, which is an unsigned car store. Then we're defining a bunch of helper functions like resize and things for dealing with indices. But the neat thing here is that we can actually expose the same API interface, same API surface. So we define default constructor, other user-defined constructor, and push, front pop, and destructor as normal. So the benefit here is that the user can transparently instantiate stack to the type of bool, get exactly the same behavior as they did before, but get more space efficiency for free, essentially. So that's quite a few functional features. So how does this exactly compare with a language like Haskell? So in Haskell, the thing to note is that first-class functions are really the bread and butter of the language. There's no oops solid classes or objects, and really the currency of programs are what we'll call really called sum and product types. So let's see this in code. So Haskell has a bit of a strange syntax for defining values and functions. So here, add and mult are delimited by this double colon, after which follows their type signatures. So add and mult are actually functions which take a float and another float and then return a float as a result. So these are binary functions on floats. Now, since this is Haskell, we can not really define simple functions like add and mult, we can also invoke higher order functions like full del prime. So full prime actually takes in as its first parameter another function, a binary reduction operation to reduce a collection. Then as its next argument takes an initial value, and then finally the list of things to combine down into a single result. And so using full del prime, this higher order function, in conjunction with our previously defined add and mult, we're able to define list sum and list prod, which respectively find the summation and product of a list of floats. But the other interesting thing is that we can also return functions from functions. So in useless sum, based on whether we pass true or false, we'll actually get back a function, either list sum or list prod. So in our main function, depending on whether we pass true or false to useless sum, we'll either get the product or summation of this list of elements 1 through 3. Now let's discuss Haskell lambdas and closures. So the syntax is actually pretty terse. So here we're invoking this transformation operation, adding this variable x or value x to the list numbers 1 through 5. And what we see here is that plus of x is actually a function. It's actually a partially applied function. So plus is a binary operation. We're binding x to its first parameter. So it becomes a unitary function. And we see that it's already lambda because in Haskell, a lambda is nothing more than a function which isn't bound to a name. And also, we're also capturing the x variable value or name from the surrounding environment to transparently create a closure. Now, how do user-defined data types work in Haskell? So this is where I get into some in product types. So here we're defining this data status, which has two constructors, sleeping or coding, which I'm sure all of you relate to. We can get even fancier. We can create so-called polymorphic data types, which are very similar to templates. So here we're defining an optional of A, which has two constructors, none, or sum of A, which takes an A and gives you back an optional of A. And then we can get even fancier. So here in stack of A, we're defining two constructors, nil, and alternatively cons, which takes an A, and then another stack of A to give you back another stack of A. So cons is essentially like a product data type. And of course, in Haskell, since there are no methods or objects, everything is based on freestanding functions. So here we define empty, pop, and push. And then here's our main function. So we can make different instantiations of these polymorphic data types. So we can have sum of 3, which is optional int, none, which is typed to be optional int. Every specialization of this polymorphic data type has its own none constructor. So we can have none, which of type optional string. And then also we can have sum of hello world, which is of course optional string. So what about specialization in Haskell? Well, actually, the interesting thing here is emulating the specializability of C++ templates is a bit more difficult in Haskell. At least in my experience, it requires a bit more fiddling with things like data families and type families. So this is definitely a win for C++ here, but I've left a link to a Godbolt which you can explore to see how this might work in Haskell. So the idea here is that C++ facilitates creating ergonomic and then transparently performant data structures for your users to use. So now you might be asking about, what about cplusplus98 template metaprogramming, right? Well, that's a good question, but that's probably left for another talk that could occupy a whole other conversation of its own. So I'll leave it out there for now. So let's recap cplusplus98. So we got functions as first-class citizens and generic programming with templates. We saw that Haskell was maybe more succinct, but it came with more painful specialization for polymorphic data types. So now let's get into C++11. The core functional features of this ISO C++ release are lambdas, stood function, stood bind and partial application, auto type deduction, and additional compile time metaprogramming. So let's start with the first one, which is lambdas. So lambdas help you to define true syntactic lexical closures. As with the things we saw before in C++98, they can easily be passed around and bound to names, so they're first-class members of this language. And as I noted, they can capture variables from the surrounding scope. They're true syntactic closures, not just emulations as we saw in C++98. The anatomy of lambda is shown here. So in the square brackets, we have our lexical captures, and the rest is essentially the same as a normal function body with parameters in round brackets and the curly brackets denoting the body or logic of the lambda. So let's explore lambdas using a string processing or file processing example. So here I'm creating a stood vector of file names representing a bunch of files on my disk. And then let's say I want to apply some transformation, say extract out those file names which correspond to actual programs like Haskell or C++ programs. And I want to filter that out into a different std vector. So for simplicity's sake, I'm assuming anything that's not .txt is a program. So I can do that as follows by invoking the std copyif algorithm and then passing to it as the filtering or predicate operation a lambda. So here I'm saying that this lambda takes in a std string of file name and it checks to make sure that the file name doesn't end in .txt. So that's our predicate defined as a lambda. We can also, of course, capture variables with pointers. So here I've refactored the example a bit to separate out into its own function. So I'm defining a function called filter files, which takes a std string, a std vector of std string, and then returns another std vector as a result. So although this is not necessarily best practice, for the sake of example, here I'm dynamically asking the invoker of this function what extension file extension they'd like to ignore the certain files on, and I'm storing that into a local variable ignored file extension. And then once again, I'm invoking std copyif, but this time in the lambda, the predicate, I'm capturing this local ignored file extension variable so that I can compare it, check to see whether the file name, the string, ends in that extension. So in our main function, now we can invoke filter files on file names, use that as initializer for programs, and as long as the user specifies the right extension type, they'll get exactly the same result. Now for std function. So std function is rather useful when you realize that lambdas are actually, every lambda is actually a unique type. So in the background of the compiler, when it sees a lambda, it's actually transparently turning it into a function object of sorts so that it can become a proper invocable. And not only are there lambdas in C++, there are tons of different callable types, right? So sometimes you may want to return one of two different callables. So std function is there to help you raise concrete function types into more general signatures so that you can use them in your programs. So essentially, they're very useful for when a desired function can only be known at runtime. So what do we mean by that? So this is an example where we're inspired by, say, streaming services. We're defining an enum class plan and a subscriber which is sub to a plan and has a boolean indicating whether they were active last month. Now, as an operator, maybe you want to define a QoS filter to give the best service to our most valuable customers. So here, QoS filter is returning a std function that takes a subscriber and returning a bool indicating whether that's a valued customer or not. So here I'm asking the operator upon which predicate they'd like to distinguish their different users. And based on their choice, if it's one, the function will either return a lambda, which takes a subscriber and checks to make sure that the subscriber is sub to the ultra plan, or otherwise returns a pointer to member, which essentially returns the boolean indicating whether they were active last month. And so in our main function, if we have a database of subscribers represented here by std vector, and we want to filter that into our lead subscribers, we can invoke std copyif and pass to it as our predicate this getQoS filter function. And the beauty here is since getQoS filter returns a more general std function type, regardless of which function is returned at runtime, it will work perfectly well, right? We don't have to worry about which function is returned. It will just return a predicate operating on subscribers. Now for std bind and partial application. So std bind allows you to create ad hoc specialized functions for more general ones. They're really great for when you know some arguments ahead of time. And case in point, when we're talking about this argument of a member function. And in general, it can do the so-called partial application for as many arguments as you need. So let's go over an example with machine learning. So a common theme in machine learning is you train a model with a bunch of training data. You have a predict function, which is able to predict on new test data. So you receive that new test data, and you'd like to transform the test data, that collection, into a set of prediction labels. So here I'm implementing that in C++ with a perceptron, which is the simplest of models. So of course, it comes with a train function, which takes in a std vector of 2D coordinates, and then a std vector of labels, -1 and 1. And of course, it has a prediction function as well. And so in our main function, we initialize a model. We train it on a bunch of training data and training labels. And then we receive some new test data, right, in the form of new coordinates. And we'd like to transform that into a collection of predictions. And we do that as follows by using std transform and passing it to it as the transformation function, the result of std bind on the address, the pointer to the predict member function, and then we're passing to it as the first argument the address of model. So that essentially becomes a this argument of the predict member function. And then we're leaving the second argument unbound by passing _1, which you get from the stud placeholders namespace. So that way, this argument will be passed in when we receive a new coordinate for each invocation of this result of stud bind. So now we get into auto type deduction. So auto type deduction allows you to bind values to names without having to explicitly give the types of everything. So it can make code more readable and maintainable when used in moderation. And it's actually a hallmark of very advanced functional languages. So here is an example in C++. In the first line, on line 4, I'm explicitly typing x to be of type double, even though I'm explicitly assigning it the value 2.0. But on the next line, I'm saying x squared is typed to be auto, so C++ will deduce for us that it is of type double using the initializer, which consists of x up times x. So type inference in Haskell works pretty similarly, at least syntactically. You can assign 2.0 to the name x, and Haskell will automatically deduce as a floating point type. Of course, in Haskell, the type inference is a bit more sophisticated since very low-level sub-expressions can inform the type of very large top-level expressions. So it's bidirectional, whereas C++ is more top-down. But that's one benefit that Haskell has as a purely functional language. So now for compile time metaprogramming and what C++11 gives us. So C++11 compile time metaprogramming essentially provided better support for what C++20 gives us in the form of concepts. It's supported by various things like variadic generics, alias templates, the decal type operator, and the type trace header. And it builds off this existing C++ behavior of substitution failures on error or SFINE that we got all the way back in C++98. So to motivate this, let's have some fun with monoids. So a lot of you may have heard of monoids and thought there's some crazy mathematical object, but really they're quite simple. It's really just a set of elements S equipped with some operation dot. This operation dot is associative so that if you have any collection of elements being combined with this dot operator, any association in parentheses will give you the exact same result. And of course, there's a left and right identity element E, which when combined with any other element gives you the other element back as a result. So in Haskell, this can be expressed very nicely. This abstract interface, this arbitrary interface we specified it in the form of this mathematical object can be expressed elegantly in the form of type classes and ad hoc polymorphism. So here I'm saying a polymorphic variable A, type A, is an instance of a monoid when it has these names or functions exported, mmempty, mappended, mconcat, which are given by these default definitions, which incidentally some of them are defined in terms of each other. And additionally, we can say that an implementer of monoid can be consist of either mmempty or mappend, or in terms of just mconcat, which takes a list of monoidal elements and combines them together monoidally. So here I'm defining two data types, product and sum, which define the monoid of the product operation, which has identity element 1, and the monoid of the summation operation, which has identity element 0 over the numbers, like natural numbers or real numbers. And so here we're actually defining product and sum to be instances of monoid. So one thing to note here is that in the type class head, we're saying num of A to constrain the concretized polymorphic type variable A so that whenever it's instantiated, it's actually an instance of an arithmetic type. And then in the product A monoid definition, we're implementing it in terms of mmempty and mappend, whereas in the case of sum of A, we're defining the monoid instance for that in terms of mconcat. And so when you get to our main function, we're able to monoidally combine a list of numbers 1 through 4, either using the product or sum monoid and get the correct results, either 24 or 10. And this works correctly regardless of how the monoid instances are defined, because we define that immutable instance either needs to export mconcat or mmempty and mappend. So that's pretty clever what Haskell does. How can we emulate this in C++? Well, first it requires a bit of template magic trickery. So I'm defining a few struct templates, monoid, product, and sum, which take a type name T parameter, and additional dummy type name parameter, which is defaulted to void, so that we can use it for SFINE. So then I'm defining the product and sum templates as follows, pretty straightforward. I'm checking here additionally that the instantiated type name T for product and sum are instances of arithmetic types by using the stood is arithmetic type trait in conjunction with the enable if T uh, uh, meta function defined by the standard library. So that's like the instance head from the Haskell type class. And then when you get to the actual implementation of monoid for product of T, we do as before with Haskell, defining in terms of mempty, which is defined out of line, and then mappend. So there's mempty and mappend. And then in the case of sum of T, we're actually choosing to implement it minimally in terms of mconcat. And so when it comes time for us to define a freestanding MMT type class method, which works on any monoid regardless of its internal implementation, here's where we use spine. So in this case, we're invoking the decal type operator to check whether the monoid is implemented in terms of MMT. And if that's the case, we have this function return the MMT static member for us. And otherwise, if the monoid is implemented in terms of mconcat, we have a different implementation so that we can calculate the identity element instance of the monoid dynamically at runtime. And so basically, we do the same dance of defining two variants for each of the type class methods, mappend and mconcat, depending on how a monoid instance might be implemented. So when it comes time to, for us to invoke a more sophisticated function like thread map, which takes a collection of elements and lifts it into a monoid to then combine them monoidally, we can invoke a function, the type class method mappend, and it'll be transparently dispatched the correct instance for us because we've already done the work of using spine to make the two variations that are possible for mappend using the decal type operator. And so in our main function, we can invoke full map using either products or sums, and we'll get exactly the same results as before as we did with Haskell. So to recap C++11, I know this is a big release. We got lambdas, stood function, stood bind and partial application, auto type deduction, and ad hoc polymorphism with templates. So now for C++14. The core functional features of this release are essentially auto return type deduction and auto lambda parameters, which are also can be considered as generic lambdas. So here in the monoid instance from before, in the default implementation of a monoid for any standard arithmetic type, where I'm just assuming sum to be the monoidal combining operator, I'm explicitly specifying in the return type of mappend that the return type is T. But in C++14, I can make it simpler by saying the return type is deduced as auto, so the T will be deduced for us based on the body A plus B. And then likewise in the monoid instance for sum of T, when I invoke the stood accumulate and pass it this lambda, I have to specify that the parameters of the lambda are explicitly instances of sum of T, given here. But in C++14, I can simplify that and use generic lambdas by saying that these are simply auto parameters, and the types will be deduced for us. And then things can get even more sophisticated, right? So in this definition of mconcat for monoids, which are implemented in terms of MMT, when we're invoking the stood accumulate and passing it this binary reduction lambda, previously we're explicitly typing the parameters to be of type element. But here in C++14, we can actually say that they are auto ampersand parameters, or universal forwarding references. So the benefit of doing that is that we can now perfectly forward each of these arguments based on their value category one by one to mappend, and we'll get the additional performance that perfect forwarding gives us. So to recap C++14, we got basic type inference and polymorphism not only based on types, but also based on this idea of value category, right? So in Haskell or languages like Haskell, this is possible, getting this dispatch on value category, but it requires working with more advanced things like layer types. So I'd say this is definitely a win for C++ here. So now for C++17. So the core functional features of C++17 boil down to basic destructuring and algebraic data types. And this can be expanded into structured bindings, stood optional, and then stood variant combined with stood visit. So let's start with the first one, which is structured bindings. So here I'm returning to my running theme of using streaming services examples. So I'm defining a struct subscriber with members ID, name, and years as member. I'm defining a simple database of subscribers represented here by a vector. And then let's say as an operator of the streaming service, I need to generate some business report, right? So I need to output the member variables of each of the subscribers in my database. So here I can do that by using a for loop. And then instead of having to use member access operators here, I'm using structured bindings to bind the member variables of subscriber to the name underscore to indicate that we're ignoring it, and then name and years as member respectively. So instead of having to rely on member access, the member access operator, we can transparently use the names we've captured in the structured binding, name and years of member, in the body of our for loop. Now for stood optional. So stood optional gives us the ability to meaningfully compose computations that have at most one meaningful result. Now, parenthetically, I have to say that this is really true starting with C++23. But essentially, it provides us with the maybe type constructor, which is from the standard library in Haskell. We saw that in the form of our custom optional of a data type we saw in our earlier Haskell example. And the neat thing here that gives us in terms of C++ programming is that it provides a value semantic alternative to misappropriating things like pointers, heap allocation, and exceptions for working with nullable values. So let's see an example of that. So here I'm defining a struct phone number, which I've kept empty for simplicity's sake, and then a class user with various standard members like age, first name, last name, email. And then you notice here I have a phone member, which is not a phone number, but rather a stood optional phone number. So this allows us to represent the fact that, say, in many services, upon, say, user registration, a user may not want to actually provide his or her phone number if that's permissible. And so we can represent that nullability by using a stood optional phone number. And then here, we're actually using a parse phone number function, which I've elided again. So you can imagine that if you take in a stood string view, which represents a phone, you have to sort of validate it, right, to check that the string actually corresponds to a valid phone. And so here we represent that by making the return type a stood optional phone number so that we can return a disengaged stood optional if it doesn't parse, doesn't validate, and return engaged stood optional if the stood string view corresponds to a real phone number. And so when we define, say, a smart constructor like make user, we can say that it returns a stood optional user so that it's only engaged when all the input parameters for the smart constructor are valid. So we're doing that validation here. So we're not really parsing the phone number and checking whether the result contextually converts this optional return contextually converts to bool based on whether it's engaged or not. We also check if the email is valid and whether the age is greater than 18. And if all of those checks pass, we return a user with all those parameters, and that is wrapped up for us into an engaged stood optional. And otherwise, we return essentially a stood null opt, a disengaged stood optional to represent the fact that these parameters didn't validate. Then finally, we have stood variant and stood visit. So a stood variant is essentially, you can conceptualize it as a type-safe generalization of enums/unions. They're a tool for defining some types from FP languages. You can note that we already got product types in the form of classes in C++. And really, as C++ programmers, what this offers us is an alternative to working with rigid class inheritance hierarchies in the world of OOP that we're used to. So to motivate this, I'm giving an example from game programming. I know many of you might enjoy video games, and some of you may even program video games. So here, you might imagine that in a video game, you might usually define a superclass called enemy, which has subtypes like slime and goblin. So instead of using inheritance hierarchy, I'm using stood variant. So I'm saying an enemy is an alias to stood variant of the type slime and goblin. So when I have my make slime constructor, I'm choosing not to return not an instance of slime, but an instance of enemy, which is that stood variant we aliased earlier. And similarly, we have a make goblin smart constructor. So we're actually combining the stood optional concept we learned before so that we can validate or input a value of hunger so that the goblin must be at least some degree of hungry. And if that's the case, we return us engaged stood optional, otherwise we don't. And so the real magic sauce of this is that we can create functions that work with these stood variants regardless of which variant is engaged at any point in time, right? And how that works is by using this bit of magic, which is taken from cppreference.com. It's basically this type struct template overloaded, which inherits from a bunch of type T's, each of which have their own call operator defined. And so if we want to define a function show which works with any enemy, regardless of which variant of the std variant is engaged, we can invoke std visit and then pass to it as the first parameter an instance of overloaded. The first argument to overloaded will be a lambda, which takes in a slime and then outputs the information for that slime. And the second argument will be another lambda, which instead works on goblins and outputs the corresponding information for goblins. And then as a second argument to std visit, we pass in our instance of the variant to the enemy E. And so basically, regardless of which type of enemy is passed, it will dispatch the correct lambda accordingly using our overloaded struct template. So here we can make slimes, make goblins, put them into a std vector of enemies, and then we can iterate over them and invoke our freestanding show function, and it will correctly dispatch to the correct lambda because we use that struct template overloaded from before. So the benefits of working with std variant like this is that essentially we can make new super types by appending types like by appending these subtypes to the list of types which are alias to other std variants, right? So if we wanted to have another higher order type like iterable, not iterable, but rather a scriptable entity, right? So if you want to have enemy be a subtype of scriptable entity, instead of going for the inheritance toolbox, we can essentially add enemy to the list of types that we're using for an instance of std variant we're aliasing to an scriptable entity. And likewise, if we want to define a new subtype for entity, we can just append a new type like orc to the std variant we defined before, which is then alias to enemy. And so the overall benefit of this is that we don't have to worry about the complications of data type layout that comes along when we work with inheritance and particularly multiple inheritance. We can have all the benefits essentially of things like multiple inheritance and complex inheritance hierarchies without those potential problems. And the additional benefit is refactoring is made very simple by the compiler errors we get improper indications of std visit. So let's recap C++17. So essentially we got basic destructuring, algebraic data types, and basically we saw that how C++17 gave us not only product types, but also sum types, right? So we got the full basket of basic data type definitions that we see in Haskell. So now for C++20, we know this is a big ISO C++ release. So here are the core functional features. So the C++20's core functional features boil down to coroutines, concepts, and ranges. So let's start with the first one, which is coroutines. So truth be told, like with pointers members before, I won't actually be spending too much time on this, but I will suffice it to note by saying that coroutines facilitate this idea of lazy computations, which is very common in a non-strict language like Haskell. If you're familiar with another functional language like OCaml in particular, this is very reminiscent of the idea of one-shot continuations. But I do feel that coroutines have an important limitation, which I felt as a Haskell programmer trying to learn this concept as a C++ programmer. Feel free to ask me more about why I feel that way after the presentation. But nonetheless, I'd highly, highly recommend you watch Dr. Ivan Chukic's talk on Proc C++ at the Meeting C++ conference for more on how you can use coroutines in a functional manner. So we're done with coroutines, let's go with concepts. So concepts are a very powerful mechanism for expressing your intent as a C++ programmer. In terms of mechanics, I'd like to think of concepts as const eval type predicate templates. So they're very similar to Haskell's type classes for expressing this notion of ad hoc polymorphism on types. So returning to the modern example from C++ 11 and 14, so before we have the struct templates take these additional dummy parameters for sphenae, we've completely done away with that. And instead of using sphenae, we're now defining a concept to ensure the instantiated types are arithmetic. So here, this concept arithmetic takes a type named t, and then checks to ensure that two instances of t can be combined using all the standard arithmetic operations that we know and love, like plus, minus, add, plus, minus, divide, and multiply. So now when it comes time to actually define the struct template product of t, instead of using type name of t as we did before, we can say arithmetic of t, so that whenever we create an instance of this struct template, the compiler will check for us that the t is indeed arithmetic in nature. And then the additional thing we can do, since we know how C++ concepts, is that we can export this idea of a monoid as a concept, right? So since before, we already know that from our use of spine for the internal mechanics of the monoid definitions, that a monoid can be, any monoid can be invoked, or rather, the typeless method mconcat can be invoked for any instance of a monoid, regardless of how exactly that monoid is implemented. So knowing that fact, we can simply say that a monoid in the C++ terms is any type for which we can invoke this freestanding typeless method mconcat. And so we have this notion of a monoid reified into a C++20 concept. I went a bit farther than I wish to. And so basically, we can use that concept as follows. So in our definition of fold map from before, we can actually check to ensure on line 221 that our instantiated type monoid is indeed monoidal in nature by using the concept we defined before. And monoidal is simply a minor improvement, or rather modification of the monoid concept to deal with constant volatile qualification. And so now for ranges. So ranges, in terms of mechanics, you define iterator synternal pair in C++. And the neat thing about them is that views on them enable lazy traversals on C++ data structures. So the additional thing is that they can be easily composed in a fluid and functional style that you usually see in the likes of languages like Haskell, OCaml, or F#. So let's go back to our running example of querying subscribers in a streaming service. So once again, I'm defining an enum class plan and a struct subscriber with various member variables, and in particular a plan member variable of type plan. And then here I'm defining a database of subscribers in the form of std vector. And then here I'm trying to define a query and extract out the target subscribers, or target demographic, based on various filters, right? So on line 32, I'm creating my std vector subscribers as a range, which std vector does indeed satisfy the concept of a range. And then I'm able to adapt it or transform it using the range adapter std_views filter, which accepts a lambda. So in the first case, I'm passing a lambda, which checks to ensure that the user is, say, under the age of 36. And then in the next instance of std_views filter, I'm checking to ensure that the subscriber is above age 24. And finally, checking to make sure whether they're not just on the standard plan. And finally, I transform each subscriber into just their first name, so I can see the first names of all my newest valuable subscribers. So if I want to generate a report out of this, I can transparently iterate over this range view of target subscribers. And the interesting thing here is that nothing actually gets computed. No computation is done until each element of this range view is demanded by the iteration of the for loop. So this is very reminiscent of a language like Haskell. So that was interesting, but it might have seemed a bit verbose in terms of syntax. So you might wonder, is this easier in Haskell? Of course, the answer is yes, because in Haskell, this is just ordinary functions and function composition. So it's exactly the same example, but now in Haskell, and we're applying the same transformations as before on our initial subscribers list, using normal higher order functions like filter and map, except that the operations are in reverse order because of the nature of the dot or composition operator. And once again, we have a for loop, and nothing is actually demanded. The elements of target subscribers are not demanded until it is needed by the for loop in which we're printing out each of those values. So to recap C++20, we got coroutines, we got concepts, and then finally ranges. So now for C++23. So the core functional concepts of C++23 are essentially std expected, std optional, and its updates in terms of getting monadic operations, additional range view library support in terms of getting things like std_views join, std_views enumerate, and then things like std generator. So let's start with stood expected. So stood expected is very similar to stood optional, but it comes with additional error tag. And it's a great tool for clarifying your intent as a programmer, in particular when you're working with what I'll call, say, failable computations. So here is an example, which I'm sure is very near and dear to all of our hearts as programmers. When we're working with arithmetic, we know tons of things can go wrong. In particular, we can have division by zero, overflow, NaN. And so what I'm doing here is appending all those types into a stood variant, which is alias to arithmetic error. And so where stood expected comes into place here. So I can define a safe divide function by taking two doubles and returning not just a double, but rather a stood expected of double tagged with the arithmetic error type. So in the body of this divide function, I can check to see whether any of these failure cases arise. And if they do, I can just throw a stood unexpected, which returns a disengaged stood expected with the error tag. And otherwise, if nothing goes wrong, I can simply return A divided by B as normal, right? And this will be wrapped up for me by C++ into an engaged version of stood expected. And so I can define normal transformation functions as before. I can have a square, which takes a double and returns the square of that double. But if I want to invoke it on a failable computation like divide, I need to do so as follows. So here I'm calling the transform method of stood expected and passing it the function square so that it can apply square to the result of the divide. So if the result of divide is a disengaged stood expected, absolutely nothing will happen. Square will not be applied. But if the result of divide was an engaged stood expected, square will be applied and that inner value will be transformed using square. And using the contextual conversion to bool, we check whether the result is indeed engaged. And based on that, we either print out the internal squared value or say that nothing happened. And so now for the monadic operation updates to stood optional. So I won't actually dwell too much on this, but I'll note that it's very similar to stood expected. You have a transform method, then also and then, which is similar to the monadic bind, which is similar to the which is exactly like the monadic bind if you're already familiar with Haskell. But basically, I'll leave it at saying that if you understand the interface and API provided by stood expected, it's very easy to transfer that knowledge over into the monadic operation updates for stood option. And finally, we get to additional range view library support. So this is where I'll demo stood views join. So here I'm invoking an example which is reminiscent of social networks. So I'm defining a struct type user. Then I'm creating a social network represented by graphs. So I'm creating different users here represented by historical figures like Ada Lovelace or Abraham Lincoln. And then I'm instantiating the graph by adding the nodes and defining the connections or friendships between our users. And so pretend as a data scientist, I want to do some query, right? Find all the second degree connections of our user Ada Lovelace. So how we might do that is as follows. So here first we create this range view first by taking user one and applying to it the method getNeighbor so that we can get a range view of the first degree connections of Ada Lovelace. And then we have an initial filter just so we don't get duplicates. And then here is where we define the next range view second. So we take first and we pipe it into stood views transform so that we can get the neighbors of each of those first degree connections so that we get a range of users. And then we apply the join operation, which is reminiscent of Haskell. So we use stood views join in order to flatten that down into a simple range of users once again. And once again, we have a filter simply for the purpose of avoiding duplicates. So of course, here's the first part and the second. And so once again, we can iterate over this range view as we would with any other traversable type in C++, and we'll get the answer as desired, all the second degree connections. So we can actually refactor this with stood views generator. So here, it actually looks a bit more imperative. So I'm defining a double nested for loop. First, it iterates over the first degree connections, then over the second degree connections of each of those first degrees. And then I actually co-yield each of those second degree connections since stood generator is actually a coroutine type. And so I can iterate over this as I would before, like I would with any other view, and I get the same result. And this is also lazy computation since nothing actually happens since the for loop dictates the demand of the values. So to recap C++ 23, we got stood expected, stood optional monadic operations, and updates to range views. So let's look at the future of FP or functional programming in C++ to round out our talk, how it will look like in C++ 26 and beyond. So the things I'm most looking forward to are things like pattern matching and destructuring, do expressions, and additional quality of life improvements to ranges. So as far as the first one is concerned, pattern matching and destructuring, this has been described with various papers over the years. If accepted in any form in a future ISO C++ standard, this would really allow programs to work on the shape of data as you normally do in Haskell and really avail of the full potential of algebraic data types. And of course, since this is C++, any such accepted implementation would certainly allow a fine-grained control of referencing and ownership transfer so we can get the benefit of using a systems language like C++. The next thing I'm looking forward to is something called do expressions. So this is described by proposal P2806. This would actually eliminate the need for immediately invoked lambda expressions for complex initialization. And basically, it would turn C++ into a far more expression-oriented language, a la Rust or Haskell. And then finally, the last thing I expect to see more of in future editions of C++ is improvements to ranges. So here are a few sample papers. One of the things I expect to see is this idea of nullable types as fallable objects. So in Haskell, the maybe type is actually a fallable, either a collection of either 0 or 1 elements. And additionally, on top of getting this idea of nullable types as fallables, I expect to see various other quality of life improvements for making working with ranges far easier. So overall, I see a very bright future for functional programming in C++. I see the language going nowhere but up. And I really see it as becoming a far more declarative, expressive, and functional language, which in no way sacrifices the low-level power and control we need as systems programmers. So I will conclude this presentation by saying that I am looking for my next adventure. If you're looking for a Haskell or C++ programmer who's dedicated to making code that is robust, performant, and maintainable, I would love to have a conversation with you. And I'd like to thank you all so much for coming to my presentation and listening to my talk. I really appreciate it. And I will end by providing you my bibliography. Thank you once again, one and all.